Hey, glad to have you back, guys. We're going to be reading another 3 abstracts from NeurIPS 2022, the medical set. First is AMOS, a large-scale abdominal multi-organ benchmark for versatile medical image segmentation. Another is class-aware adversarial transformers for medical image segmentation. And the third is benchmarking heterogeneous treatment effect models through the lens of interpretability. So let's get started on AMOS, a large-scale abdominal multi-organ benchmark for versatile medical image segmentation by Yuanfeng Ji et al., coming from the University of Hong Kong. And their brief says a large-scale abdominal multi-organ benchmark for versatile medical image segmentation. The abstract reads, despite the considerable progress in automatic abdominal multi-organ segmentation from CT MRI scans in recent years, a comprehensive evaluation of the medical data, evaluation of the model's capabilities is hampered by the lack of a large-scale benchmark from diverse clinical scenarios. Constrained by the high cost of collecting and labeling 3D medical data, most of the deep learning models to date are driven by data sets with a limited number of organs of interest or samples, which still limits the power of modern deep models and makes it difficult to provide a fully comprehensive and fair estimate of various methods. To mitigate the limitations, we present AMOS, a large-scale, diverse clinical data set for abdominal organ segmentation. AMOS provides 500 CT and 100 MRI scans collected from multi-center, multi-vendor, multimodality, multi-phase, multi-disease patients each with voxel-level annotations of 15 abdominal organs, providing challenging examples and testbed for studying robust segmentation algorithms under diverse targets and scenarios. We further benchmark several state-of-the-art medical segmentation models to evaluate the status of the existing methods on this new challenging dataset. We have made our datasets benchmark servers and baselines publicly available and hope to inspire future research. They have a GitHub page that's available from the link that I will put in the description. And also I'll put a link to the NeurIPS webpage where you can access this poster and their paper and supplemental information. All right, that is the first one. The second one is benchmarking heterogeneous treatment effect models through the lens of interpretability by Jonathan Crabbé et al. And their brief says, we construct a benchmarking environment that allows us to empirically investigate the ability of personalized treatment effect models to identify predictive covariates. And their abstract reads, estimating personalized effects of treatments is a complex yet pervasive problem. To tackle it, and recent developments in the machine learning ML literature on heterogeneous treatment effect estimation gave rise to many sophisticated but opaque tools. Due to their flexibility, modularity, and ability to learn constrained representations, neural networks in particular have become central to this literature. Unfortunately, the assets of such black boxes come at a cost. Models typically involve countless non-trivial operations, making it difficult to understand what they have learned. Yet, understanding these models can be crucial. In a medical context, for example, discovered knowledge on treatment effect heterogeneity can inform treatment, prescription, and clinical practice. In this work, we therefore use post hoc feature importance methods to identify features that influence the model's predictions. This allows us to evaluate treatment effect estimators along a new and important dimension that has been overlooked in previous work. We construct a benchmarking environment to empirically investigate the ability of personalized treatment effect models to identify predictive covariates that determine differential responses to treatment. Our benchmarking environment that enables us to provide new insight into the strengths and weaknesses of different types of treatment effects models as we modulate different challenges specific to treatment effect estimation. Example, the ratio of prognostic to predictive information, the possible nonlinearity of potential outcomes, and the presence and type of confounding, I guess their abstract is a little lacking. That's where it ends. But I will have all the links to this poster and paper in the description and in this video. All right, and let's read the third. This one is Class-Aware Adversarial Transformers for Medical Image Segmentation by Chenyu et al., coming from Yale University, UT Austin, and University of Oxford. And their brief says, we propose a GAN model for the first time using a transformer-based architecture to address 2D medical image segmentation. Okay, and their abstract reads, transformers have made remarkable progress towards modeling long-range dependencies within the medical image analysis domain. However, current transformer-based models suffer from several disadvantages. 1. Existing methods fail to capture the important features of the images due to the naive tokenization scheme. 2. The models suffer from information loss because they only consider single-scale feature representations. And 3. The segmentation label maps generated by the models are not accurate enough without considering rich semantic context and anatomical textures. In this work, we present CastFormer, a novel type of adversarial transformers for 2D medical image segmentation. First, we take advantage of the pyramid structure to construct multi-scale representations and handle multi-scale variations. We then design a novel class-aware transformer module to better learn the discriminative regions of objects with semantic structures. Lastly, we utilize an adversarial training strategy that boosts segmentation accuracy and correspondingly allows a transformer-based discriminator to capture high-level semantically correlated contents and low-level anatomical features. Our experiments demonstrate that CastFormer dramatically outperforms previous state-of-the-art transformer-based approaches on 3 benchmarks, obtaining 2.54 to 5.88% absolute improvements in DICE over previous models. Further qualitative experiments provide a more detailed picture of the model's inner workings, shed light on the challenges and improve transparency, and demonstrate that transfer learning can greatly improve performance and reduce the size of medical image data sets in training, making CastFormer a strong starting point for downstream medical image analysis tasks. All right, and I will have this also in the link to this paper and page on NeurIPS website. I'll have that available for you, and any other links that I can find to their GitHub pages, and also to their NVIDIA GPUs in case you're looking for a new GPU in the market. All right, guys, thanks for joining, and I will catch you on the next round. All right, have a good day. Bye-bye.